I don't have my. So we're looking at 0.100 moles of sodium nitrite to 1.00 liters of
HNO2 aqueous.
Okay, what's the concentration of HNO2?
100 molar.
0.100 molar HNO2?
Yes.
Okay.
The pH change. We want the pH change ultimately.
All right. So first thing is you figure out what the pH of this is. The pH of this is just Ka and Kw. Do you think you're going to have to worry about Kw for this particular acid at this concentration? No. And so just Ka, and so you figure out the pH. Is there any problem with that, or this is a chapter 16 style? You know, you do chapter 16 style calculation here to determine the pH. And then when you add this, then you have a mixture. And so when we add those two together, we're going to get 1.00 liters. And this is adding moles, so we're going to assume the volume doesn't change. If the volume doesn't change, we're going to have 0.100 molar HNO2 and 0.100 molar NaNO2. This is convenient because we don't have to do a solution dilution here. If we just add the moles and assume the volume doesn't change.
Why do we make the assumption that the volume doesn't change?
Because they're saying add moles of this, which means they're not saying add this many milliliters, they're saying add moles.
Okay.
Okay, so we have this, and what kind of mixture is this? You have to get good at recognizing mixtures in this chapter. This is a weak acid. What's sodium nitrite?
A salt.
Okay, it's a weak base.
Salt of a weak base.
But there's something special about this mixture. What is special about this mixture?
Buffer. HH buffer.
Yeah, this is an HH buffer. It's a weak acid, weak base mixture, and they're conjugate pairs of each other. So we can just use the HH equation. pH is equal to pKa of HNO2 plus the log. And so it's 0.100 of the base, which is nitrite, over 0.100 of the acid, which the log goes to 0. So the pH is just equal to pKa. And so when they're asking for the difference, you calculate the pH before, and then you calculate the pH after. pH is going to go up a little bit because we're adding base to this, weak base.
Oh, I get it.
You got it? Okay.
Yes.
That's all you do in that particular chapter.
So it's like chapter 16 and 17 together.
Okay, was there another question? No.
Thank you.
Sure. So we're going to look at titrations. And so here is the titration curve. We're starting off with strong acid, pH is about 1, and we're neutralizing with a strong base, sodium hydroxide. And so the base goes into the burette, sodium hydroxide, so we just add the titrant, sodium hydroxide, to the acid, which is in the beaker or the flask. And the pH is going to stay low because here, we don't have enough acid. We don't have enough base to neutralize all the acid. And so this is excess acid. And then we hit the equivalence point where we get salt, sodium chloride, and water. Sodium chloride is neutral, so that should be pH 7. And then we go with excess base. What's overlaid here are different indicators that we could use. So if we use phenolphthalein, and we saw the phenolphthalein changes color around pH 9. The equivalence point is at pH 7, so there's a pretty big error in terms of pH. But in terms of milliliters, is there much error? No, there's barely any error in terms of milliliter because this line is practically vertical. All right, now we're going to look at the inverse of that, which is now we're going to put the acid in the burette and the base in the beaker or the flask. And so here, if we have the base initially, and then we're titrating with acid, then it's just going to look inverted. That is, we're going to start off at high pH 13. Equivalence point is still going to be 7, and then we're going to go to excess acid. So we go excess base, neutralize, excess acid. All right, this is a weak acid, and so the same thing. Here we're going to have excess acid and neutralize. But when we neutralize a weak acid like acetic acid, the salt that we generate, sodium acetate, is not pH 7. Sodium acetate is actually a basic salt, and so the pH at the equivalence point, the point of neutralization, is actually going to be about 9 here. And then we have excess base. And so when we look at this, phenolphthalein is actually pretty good because there's going to be minimal error in terms of pH and minimal error in terms of volume here. And so phenolphthalein looks like the perfect indicator for something like this titration. And so let's take a look at this titration in detail. We're going to do all the types of calculations that are going to be involved with a weak acid. Strong base titration. So we'll just use acetic acid like that. I'm going to use not 25 milliliters. 25 milliliters would be half a burette. We're going to use 30 milliliters to hit the equivalence point. And so what I'm going to do is I'm going to put here initially 30.00 milliliters of acetic acid, and we're going to keep the concentrations simple. So this is going to just be 0.100 molar acetic acid here. And then we're going to put some 0.100 molar sodium hydroxide in the burette, and then just add this. There's going to be a pH probe in here. We'll monitor the pH. And so what our curve is going to look like is structure will look quite similar to this. Only difference is where the equivalence point comes. And so over here, the equivalence point came at 25 milliliters. Ours, well, how many milliliters of sodium hydroxide will I have to add to neutralize 30 milliliters acetic acid? The same amount, right? I'm going to have to add 30 milliliters because they're both the same concentration. So if I want to neutralize all this acetic acid, I'm going to have to add 30 milliliters of the sodium hydroxide. And so at 30.00 milliliters, I expect to see the equivalence point be up here. The equivalence point is going to have a pH greater than 7 here. And so the curve is going to look something like this. 0.100 molar acetic acid with no base added. It's just 1.100 molar acetic acid is going to have a pH about 2.8 something. I forgot the exact number. And then the pH is going to climb up a little bit, but we still have excess acid, so the pH stays low. And then the pH rises up here to the equivalence point. But we're not going to stop at the equivalence point. What happens is a lot of people, when they see that pink color, they stop, because in Chem 1A, that's where you stop, right? But if we were to stop here, we're going to miss the whole second half of the pH titration curve. And then we can't analyze it properly. And so what we have to do is we have to continue on. And so this is why we only calculated the equivalence point at 30 milliliters, because we want an additional 20 milliliters of titrant to complete the curve. And so what we're going to do is we're going to just keep adding, and then we're going to get into this excess base, and then the pH is going to flatten out. But even if it flattens out, like when you go into lab tomorrow, you're going to see, pH flattens out. And so you add a milliliter, the pH doesn't really change much, right? Add a milliliter. But what we're going to do is we're going to carry this all the way out to, 45 or 50 milliliters, depending on where you started. And so we go out to, let's say, 50.00 milliliters. Here, it's kind of flat, so you can increase the interval between data points. And that is, here, around the equivalence point, we want it drop by drop, because this whole thing is going to happen within 1, 2, maybe 3 drops. And so if it happens in 1, 2, maybe 3 drops, we got to make sure we're going drop by drop, otherwise we're going to miss it, because if we take 20 drop intervals, that is 1 milliliter intervals, we're going to miss the whole thing. We don't know exactly where it occurred within that 20 drop interval. Did it occur on drop 1 or drop 2 after that, or drop 3. And so we want to figure out where this occurs in terms of milliliters here. And then continue on. So out here, we might increase the interval to like 5 milliliter intervals so that we can just use the rest of the sodium hydroxide in our burette. And so you can see here they carried this titration out to 50, even though the equivalence point only happened at 25. Right? Well, we're going to have it at 30 because not much happens once we plateau. But we got to see this plateau and how it behaves. And so that's important. And so at 30.00 milliliters, we call this the equivalence point. And so there are some other important volumes here. 1/2 this would be 15 milliliters. And so at 15.00 milliliters, we call this the half equivalence point. And so that's an important point in the titration. We want to know, what the pH is, halfway to the equivalence point. And then we have some other points in here that we want to predict. At 7.5 milliliters, that would be called the 1/4 equivalence point. And then at 22.5 milliliters, we would have the 3/4 equivalence point. And so the half, the 1/4, 3/4, those are all important for us in mapping out the curve. And then there are a couple of other ones that are important. Here and here. So we want the 1/4, the 1/2, the 3/4, and we also want the well, we did that one just for a calculation, just to see, how tight this is. We got to point them right around here. But the other one we want is called the 1/11th equivalence point. We want that. And so at the 1/11th equivalence point, what is the volume? Well, if we look at the volumes, at the half equivalence point, it's half the volume, right? At 1/4 of the equivalence point, it's 1/4 of the volume. So at the 1/11th equivalence point, it's got to be 1/11th the volume. And so what is 1/11th of 30.00 milliliters? What is it? 2.72? Okay, so at 2.72 milliliters, we should have the 1/11th equivalence point. And over here, we want one more. We want something called the 10/11th equivalence point, where we've neutralized 10 parts out of 11 parts total. 10/11ths is also called it's 90.9% neutralized, 90.9% neutralized. At the 1/11th, it's 0.909% neutralized, or about 1% neutralized. And so over here at the 10/11ths, what's the volume at the 10/11ths equivalence point? 27.27 milliliters. Okay, so that's actually going to be out there. And so we want the 1/11th and the 10/11ths equivalence point. Okay, then we want the equivalence point, and then we want some point out over here. And so we'll go out, let's just go out maybe to 35 milliliters here. Or, we could go out to 50 milliliters, it doesn't matter. We're just going to get some point in this area here. And so we're going to do some calculations. So we're going to predict what the pHs should be based on the calculations. And so we're going to calculate the pHs of all these, except for this. This one, the pH is 2.8. This is just a chapter 16 style calculation, just acid, acetic acid, 0.100 mole. The other type of calculation is we're going to try to figure out what the volume is for a specific pH. So, for example, if I want to, let's say, if I want pH 5.00, at pH 5.00, where am I? Well, I'm between the initial, just acetic acid, and the equivalence point. So it's somewhere in this range here. This range is called the buffer region here. And the buffer region is going to extend just past this and just this point here. And so this is in there. And so in order to get a pH of 5.00, you know, how many milliliters of sodium hydroxide is that? Where am I? Here. And then we're going to do one more calculation. If I want a pH of 12.00, 12.00, I must be past the equivalence point. Past the equivalence point, this is called the excess strong base region. And so this is the excess sodium hydroxide region. And that's going to extend past the equivalence point here. And so if I want a pH of 12.00, you know, how many milliliters of sodium hydroxide do I have to add in this titration? And so we're going to calculate that. And so let's go ahead and do these calculations. So. All right, so the first calculation we're going to start off with is at the half equivalence point here. And the way we're going to do that is we're going to do that like any other calculation in this chapter, and that is, okay, we start off with 30.00 milliliters of 0.100 molar acetic, and then we're going to add 15.00 milliliters of 0.100 molar sodium hydroxide. When we do that, we're going to end up with a total volume of what? Yeah, we're going to have 45.00 milliliters, and that means we have to recalculate the concentrations, and that is the acetic acid concentration is going to be a 30.00 to 45.00 dilution of 0.100 molar. And so 30 to 45 dilution is actually a 2/3 dilution, which is going to give me 0.0666 sub 6 molar. And then I recalculate the sodium hydroxide solution, which is going to be 15.00 over 45.00 dilution for 100 molar. And that's going to give me 0.03333, 2/3 dilution. So this is, 1/3 dilution. 2/3 dilution, 1/3 dilution. Here. Okay, after I do step I, then I'll go to step 1, which is going to be the strongest acid plus the strongest base. So the strongest acid is going to be acetic acid. Strongest base is sodium hydroxide. This is going to produce sodium acetate and water. K for this is what? And so this reaction is going to go to completion. So let's go ahead and plug in. So we're in the excess acid. So we haven't neutralized all the acid. We're going to have some acid left over because we didn't add enough base. We got 0 molar here. And so the change is going to be complete. What's the limiting reagent here? This is sodium hydroxide. Sodium hydroxide is completely consumed. 0 molar. And so this is going to be minus 0.03333. This is going to leave me with 0.03333 molar here and 0.03333 molar here. All right, that's step 1. Now I go on to step 2. When I go on to step 2, I have to recognize this. You take a look at the mixture that's left over. What is the mixture left over? The mixture left over is acetic acid and sodium acetate, which is a buffer. And so the reason we call this the buffer region is not because it's a buffer initially, it's because what it forms is a buffer. And so when I look at this, when I start off, is acetic acid and sodium hydroxide itself a buffer? No, because this is a strong base, weak acid. This is not a buffer. But you know, these are gonna react. You can't stop the collisions from happening. And once they react, then we're left over with a buffer. The product is a buffer. And so here, this is what kind of buffer? This is a HH buffer, a Henderson-Hasselbalch buffer, because the weak acid and the weak base are conjugates of each other. And so if we have a Henderson-Hasselbalch buffer, then the pH is equal to the pKa of the acid. In this case, the acid is acetic acid, plus the log of the base to acid ratio. The base is the acetate, and the acid is acetic acid. And so log of 1 is actually, it's 0, so the pH is just equal to the pKa. The pKa of acetic acid is 4.742. Just 4.7. We'll just go with 4.74.
Wasn't it the initial concentrations? For the log?
It is, because it's not the initial concentration. This reaction happens completely because K is very, very large. And so the next thing is, well, we have a weak acid, we have a weak base. And so what should we do with the next step? The next step we should do Ka. Let me ask you this, should we do Ka for acetic acid? Or should we do Kb for sodium acetate? Or should we do both Ka and Kb? What should we do? You're right, we do either one, either the Ka or the Kb. But did I do it? I didn't do it because the Henderson-Hasselbalch, I just take the initial concentrations of what the Ka ice table would have had and skip the ice table entirely. And so these are the initial concentrations for the next step. And so that's where I got it. These are the, because I'm left with something mu here, and then something mu is the Henderson-Hasselbalch buffer. So the pH is just equal to pKa here. When I'm in the buffer region, there's a shortcut method I can use. Do I have to worry about solution dilution for buffers? If I were to dilute a buffer, would that change its pH? If you look at it, the pH just depends on the ratio. And so if I were to add the same amount of water to both of these, because the ratio wouldn't change, right? Because both the acid and base are in the same beaker. And so solution dilution doesn't impact. So if I dilute this tenfold, so it goes 0.003 and 0.003, it doesn't matter. It's going to give me the same pH. And therefore, we don't have to worry about solution dilution with buffers. And there's going to be a shortcut method. And so this just applies to the buffer region. And again, the buffer region is this region right after the initial, to right before this. Even though this doesn't look like a very good buffer, does it? This is just one drop or less than one drop. And so this buffer region shortcut method is going to look like this. And so what we're going to do is we're going to go with the 1/4 equivalence point. The 1/4 equivalence point. At the 1/4 equivalence point, how much of the acid have I neutralized? 1/4. You know, I just have 7.5 mils out of 30 mils required. This was 1/4. And so I've neutralized 1/4 of the initial acid. And so I'm just going to set up a generic, acid. This is some generic weak acid with a strong base like sodium hydroxide. And so this is going to give me sodium A plus H2O liquid. I'm using generic because this works for any weak acid, strong base. This is monoprotic. And so if I have HA initial and then my sodium hydroxide initial, this is what's going to happen. So I neutralize 1/4 of my initial. And so that means I'm going to lose this. I'm going to lose 1/4 of my initial. And so that means how much do I have left over? I have 3/4 of my initial left over, right? And then over here, this started off at 0, so this is going to be 1/4 of the initial. And so this is going to give me so NaA concentration. This is going to go down to 0 here. And so now I see the ratio here. This is an HH buffer. And so the pH is equal to the pKa plus the log of the base concentration, which would be 1/4 of the initial, over the acid concentration, which is 3/4 of the initial. And so this is pKa plus the log of, well, 1/4 divided by 3/4 is 1/3. And so this is going to be pKa, and the log of 1/3 is actually minus 0.477. What's that? Yeah, you can do it that way too. And so this comes out to, it's going to be the pKa minus about 1/2, or 0.477. And so when we look at the titration curve, we can get these points quite quickly. So here it's a 474. At 7.5, well, ours would be 7.5 because we offset it, or whatever it was. It would be 4.74 minus 0.477. Let's go to the 3/4 equivalence point. At the 3/4 equivalence point, then we take our generic. You see it already? The liquid. And so here we have our initial, this will be 0, and we're going to lose 3/4 of our initial. And so that leaves us with 1/4 of our initial left unreacted. But we're going to gain 3/4 of our initial here. The sodium hydroxide is completely consumed, so it goes to 0. And so we end up with this ratio. 1/4 to 3/4 ratio. Yeah, it's going to be the opposite. So pH is going to equal to pKa plus the log of, now it's 3/4 base on the top. The initials cancel, so it's going to be 3/4 to 1/4 ratio, which is equal to the log of 3, which means it's going to be the pKa plus 0.477. And so these points are very easy to get. The 1/4 is pKa minus 0.477, the 3/4 is pKa plus 0.477. The volumes would differ here because the total volume is 25, so 1/4 of 25 would be, and 3/4 of 25. For us, it was 30, so 1/4 of that. Was it 30 or 35? 30. And so why did I do the 1/10? What was special about the 1/10 equivalence point? You know, it seems odd. Not 1/10. It wasn't 1/10. What was it? 1/11. 1/10 seems reasonable. 1/11 seems odd, doesn't it? And so why did I do the 1/11th equivalence point? And so can you do the same thing and just calculate what the pH is going to be at the 1/11th equivalence point? So why don't you go ahead and do that? And so 1/11 is, we've just neutralized 1/11 of our initial, which means we're going to have how many left over? 10/11 of our initial left over. And then we're going to generate 1/11 product. This is going to go to 0. And so take a look at the ratio. It's a 10-to-1 ratio. And so we have 10 parts of unreacted acid. And 1 part of product. And so when we do this, well, this is going to be a Henderson-Hasselbalch buffer. And so when we do this, we got the pH is equal to pKa plus the log of 1/11 over 10/11, which means it's going to be the pKa plus the log of 1/10. And so this gives us a base to acid ratio of 1:10. And so what we have to look at is how the base to acid ratio compares to the equivalence point. And so the way we understand that is, okay, this is the base to acid ratio. And how it compares to the equivalence point is like this. If we have 1 part base and 10 parts acid, that means we must have a total of 11 parts. If we have a total of 11 parts, then that means, 1 out of the 11 parts was converted into base. And that means 10 out of 11 parts remained as unreacted acid. You see that? And so this is the relationship between these. So we just connect them together. Here. And so going through this, if we have a base to acid ratio of 1:10, that's just pKa minus 1. And then the 10/11ths will be plus 1, pKa plus 1. And so this is why the 1/11th and the 10/11ths are important, because we go pKa minus 1, and pKa plus 1 here. And pKa plus or minus 1 is in this kind of the flat region of this. If we go beyond that range, then we have either too much acid or too much base, right? So it becomes a lopsided buffer. pH can change more dramatically. And so that's what we see here. But, even though we like to keep the buffer range, pKa plus or minus 1, the Henderson-Hasselbalch is valid over a much wider range. And so we could use the Henderson-Hasselbalch equation for pretty much all the calculations in this range, even if the pH goes quite high here, quite low there, outside the plus or minus. Let's do the next calculation. The next calculation is going to be at how many milliliters will I get to a pH of 5.00? Well, pH of 5.00, where is that in the titration curve? Well, if the pK is 474, then 5.00 is in the buffer range, right? In fact, it's nicely in the buffer range. And so, first thing is, this is in the buffer region. If it's in the buffer region, then it's going to be described by the Henderson-Hasselbalch equation. And that is pH is equal to 5.00, which is equal to pKa, plus the log of the base to acid ratio. Well, the pKa is 4.74. What's that? And so the log of the base to acid ratio is equal to 0.26. And that means the base to acid ratio is equal to 10 to the 0.26 power, which is 1.81? Okay, 1.819. Okay, which means that we have 1.819 parts base to 1 part acid. Which means that the total number of parts must be equal 2.819 parts. Okay? Which means that 1.819 out of 2.819 parts were converted into base, and we have 1 out of 2.819 parts remaining as unreacted acid. This amount that's converted into base, this is what we call our equivalence point. This is how much reacted. And so what we say is this has got to be the 1.819 out of the 2.819 equivalence point, whatever percentage that is. And so it's more than 50% neutralized. Do you see that? It's like, I don't know if we convert that into percentage. Well, if we want to figure out the volume, then, the fraction that was neutralized is 1.819 out of 2.819 times a total volume of 30.00 milliliters, which gives us how many milliliters to get to that pH? 19? 19.36. And so at 19.326 milliliters, we should hit 5.00 for pH. So in other words, the numerator is the amount reacted, the denominator here is the amount unreacted. And the fraction reacted, the fraction unreacted. The equivalence point is what fraction is reacted. Okay. All right, now let's go to the equivalence point. The equivalence point is outside the buffer region. This is no longer a buffer, so we have to worry about solution dilution. And so we're going to do it like we normally do it. That is, we're going to take our 30.00 milliliters plus how many milliliters base? 30.00 milliliters of base acid. And so this is going to give us a total volume of 60.00 milliliters. And so we do our initial step here, which is going to be the solution dilution. Is we'll take our acetic acid, and it's going to be a 30.00 over 60.00 dilution of 0.100 molar. I'm just going to just cut that concentration in half to 0.0500 molar. The sodium hydroxide is going to see the same dilution factor, so it's going to be 0.0500 molar. So this is a 1-to-2 dilution. Okay, then we'll take the strongest acid, acetic acid. What's the strongest base? Sodium hydroxide. It's going to form sodium acetate. Y. 0.0500 molar, 0.0500 molar. The reason why we call this the equivalence point is because we have equal amounts of both. In this case, equal concentrations. And so this is stoichiometric. And so it's going to neutralize. K is very, very large. We end up with 0.0500 molar sitting that state. Well, you have to recognize this, what we're left over with. What we're left over with is a base, right? Weak base. That's it. So if we've got a weak base, then we look for all the hydroxide producers, starting with the biggest one. So for our next step, we wouldn't use the Henderson-Hasselbalch because we don't have any acid. We use the Kb. So the Kb is going to be C2H3O2 minus plus water. This is going to produce acetic acid and hydroxide. Kb for this is equal to Kw divided by the Ka for acetic acid, which is 1.8 times 10 to the minus 5. This gives me 5.5, so 5 times 10 to the minus 10. All right, so let's go ahead and plug the initial in here, 0.0500 molar, 0 and 0. Minus x plus x plus x, so 0.0500 minus x, and x, and x. We solve for x here. So this is going to be the acetic times the hydroxide divided by the acetate. So this is going to be x squared over 0.0500 minus x. We're going to try the simplifying assumption. See if it works. So this is going to be x squared over 0.0500. Which gives me an x of what? Five point 5.26 times 10 to the negative 6. If we look at the percent change, this is 10 to the minus 6 change over 10 to the minus 2 initial times 10 squared, which gives us about 10 to the minus 6% change. And so the SA is no problem, right? Is that right? No. I made a mistake, didn't I? 10 to the minus 4. 10 to the minus 4%. So that's no problem. And so what I'm going to end up with here is 1, 2, 3, 4, 5 zeros and a 526 molar hydroxide. Since I'm interested in pH, right, this pH titration, I probably should put in the rest of these and then double check the K, right? This would be 5.26. This is going to be 0.0500 minus 0. And then check the K, that checks out. Good, right? Did it? It's good? Okay. All right, now we have to look, I mean, this is a base solution, so we have to look for all the hydroxide contributors. And so what would be the next hydroxide contributor after acetate? Water. All right, this is times 10 to the minus 6. So should we worry about Kw? You know, what's the most hydroxide we're going to get from Kw? 10 to the negative 7, but you know, will you ever get 10 to the negative 7? No, you're never going to get 10 to the negative 7 because that would be if there's no common ion. But now there's common ion, which is this hydroxide here, which is going to be 10 to the minus 7. It's got to be less than 10 to the minus 7, more like 10 to the minus 8, 10 to the minus 9. So should we worry about the hydroxide we get from Kw? Yes, no, or uncertain? I would say no. I wouldn't worry about it. I wouldn't worry about it until this got to like, no, negative 5, I'd even worry less. It's got to get smaller. If this were 10 to the negative 7, I'd probably start to worry. 10 to the minus 8, I'd start to worry. You know, because then water could be a significant contributor of hydroxide to this. But the more concentrated this, the less we have to worry, right? If this were 1 molar, then the amount from it. So do you agree with me? Just skip Kw then? Yeah. We could do it. The morning class, not everybody agreed. And so we did it. And if we did Kw, we'd add like it'd be 6, one more digit and then a 1 out here or something. And pH was no different. So we actually did and saw it was negligible. Which is good because if we got a significant amount from Kw, you know what that means? Simultaneous. Which, and so what we're going to do here is we're going to assume that Kw should be negligible here. And then figure out what the pOH is. So can somebody calculate the pOH? What did you get? 2.78? 5.278, which means the pH is 8.721. So the pH comes at about 8.7. Phenolphthalein turns at about 9. That's really close. 8.7 and 9. So the end point and the equivalence point for acetic acid titration with phenolphthalein should be just about spot on. Okay. That's good. And so that would be the pH at the equivalence point. Now we're going to add excess base. And so we'll be left over with excess sodium hydroxide. Let's do that in the next calculation. So this is this plus, we did plus how many? 35.00 milliliters of sodium hydroxide? Is that right? Yeah. And so this, yeah, it's going to give us a total volume of 65.00 milliliters. And so let's calculate the acetic acid. The dilution for the acetic acid will be a 30.00 over 65.00. And this is not the cleanest number. No, I should have done 40, or it would be, well, it'd be a lot cleaner. Do you want to do it? Yeah? Okay. All right, we'll skip this, and then we're going to replace it plus 40.00 milliliters. because then the numbers are going to be a lot simpler. And so this will be, or will it be simpler? I don't know. This is going to be 70.00 milliliters, right? And so that means the acetic acid is going to be a 30 to 70 dilution of 0.100. Maybe it isn't. This is not any cleaner. But it's all right. We stuck with 40, so let's just do it. 3/7. 3/7 is what? Okay, so this comes out to 0.4285. Not clean at all. Sorry. 40 is not cleaner. And then the other one is going to be a 40 over 70 dilution of 0.100 molar, which is going to give us I'm sorry, what is it? 0.5 something? Five seven. 0.0. So this is 0.0. Okay, so this is 0.05714. Okay, this is not clean at all. It's okay, we'll just stick with this. So we'll take our strongest, you see we started each of these problems over again. So here, we're going to neutralize all our acid because now it's going to be the limiting reagent. We're going to have some base left over, some sodium hydroxide left over. And so the acid's the limiting reagent, so that goes to 0 here. And so that we're going to lose all of it. This is minus 0.04285 molar, which should give us what? 0.01429. And 0.04285 molar. And so take a look at what's left over, and what do we have left over? We have a strong base and weak base. Strong base, weak base. If we have a strong base, weak base, then it's a base mixture, so we look for all hydroxide ion contributors. And so the biggest hydroxide ion contributor to this will be sodium hydroxide. Then we ask ourselves, will acetic acid be a significant contributor or an insignificant contributor to that? It's going to be insignificant. And one reason why is, what is Kb for acetate? 10 to the minus 10. 10 to the minus 10 is not very strong as far as base. And so with a Kb of 10 to the minus 10, I would say acetate is going to be totally insignificant. This would change, of course, if the Kb were larger. You know, if the Kb here for the weak base were like 10 to the minus 2, then would you worry about the hydroxide coming from the weak base? Yeah, you would worry about it. And so, you know, in a stepwise fashion, this is going to contribute very little. And so, this we'll just say this weak base has a KB of about 10 to the minus 10, which means it should be insignificant, therefore insignificant contributor of hydroxide. This. And so we're going to stop here with the calculation and figure out the POH. The POH is going to be the negative log of this, because we're going to say, and then KW, we're also ignoring KW because, I mean, well, KW is 10 to the minus 14, so that should even be less. And so what does it come out to? 1.844. Is that right? And that means the pH is equal to 12.156. 12.156. So we'll hit a pH of 12.156 now. All right, the last problem was this. How many milliliters will it take to hit a pH of 12.00? Well, to hit a pH of 12.00, I'm going to need less than 40 milliliters, because with 40 milliliters, I get the pH of 12.156. And so I got to figure out how many. And so basically what I'm going to do is I'm going to work backwards here. I'm kind of going to work backwards and work forward. You'll see in this particular problem. And so the first thing is, this is the total, what's that? If I have a pH of 12.00, does that mean that the hydroxide ion concentration would be 10 to the minus 12.00 molar? Is that right? 10 to the minus 12 is 1.0 times 10 to the minus 12 molar hydroxide. Actually, I made a mistake. Do you see it? Right. So not this, because I need to go from pH to POH. And the POH would be 2.00. And that means the hydroxide is going to be 10 to the minus 2.00, which is going to be 1.0 times 10 to the minus 2 molar. Okay, is that right? All right, now I have to figure out how many steps do I have to work backwards from. So do I put this at the final step, where KW, step 3? Or do I ignore KW and put this at the final step of K2, which, I mean, step 2 would have been acetate. No, we already ignored acetate and KW, right? And so what I'm going to say is that acetate and water are going to be insignificant contributors. And so all this hydroxide is going to come from the sodium hydroxide, excess sodium hydroxide. And so that means I'm just going to plug it in here at the end of step 1. Now, if the others were significant contributor, I'd have to start down lower. But here, I'm just going to say, well, this is going to be 1.0 times 10 to the minus 2 molar. And then I expect insignificant additional hydroxide from whatever acetate I have and whatever water is, right? And then I've got to work backwards. And so I have to work backwards. Well, how do I work backward from this? So what I'm going to do is I'm just going to start from the beginning, like we do for all these problems. And so when I start from the beginning here, I have 30.00 milliliters of acid. And then I'm going to add how many milliliters of base? I don't know how many milliliters of base, so I'm going to call it Z milliliters of sodium hydroxide. And this is going to be my acetic acid here. And so this is going to give me a total of 30.00 plus Z milliliters. And then what's the next step after this? Solution dilution. And so what we want to do is we want to figure out what we call the initial concentration of acetic acid is. Because that's going to go here. The initial concentration of acetic acid is after solution dilution. And that acetic acid, well, it's going to be a 30.00 to 30.00 plus Z dilution of 0.100 molar. Okay, then I need the sodium hydroxide concentration. Now, this dilution factor for the sodium hydroxide is going to be Z over 30.00 plus Z. That would be my dilution factor of 100 molar. Okay, that's what I would plug in here. That would be the sodium hydroxide initial. And the sodium acetate initial is 0 because nothing's happened yet, right? We haven't reacted them. Okay, next what? Well, next I'd have to do this. This is going to just be minus X, right? Minus X plus X, correct? And so, you know, over here I just get the initial minus X, and over here it'd just be X, right? And then this sodium hydroxide is just going to be the NaOH initial minus X. Is that right? But you know what X is. What is X? X has to be what? Yeah. X has to be acetic acid because this is the limiting reagent. We're in the excess base, and so this has to go to 0. Therefore, X has got to be the concentration of acetic acid initial, right? And so what we're going to get is this. If X is the concentration of acetic acid initial, because this go, then that means that 1.0 times 10 to the minus 2 molar is equal to the concentration of sodium hydroxide initial minus the concentration of acetic acid initial. Well, let's go ahead and substitute the concentration of sodium hydroxide initial is just Z over 30.00 minus, or excuse me, plus Z times 0.100. Okay, minus the concentration of acetic acid initial is 30.00 over 30.00 plus Z times 0.100. And then we just solve for Z. Z is the number of milliliters of sodium hydroxide we have to add, and that's what we're after. You know, how many milliliters of sodium hydroxide will it take to hit this pH? And so these are the basic types of calculations that we do for weak acid, strong base titrations. All right, any questions on this? When we go to polyprotic acids, it's just a little bit more complicated. For example, this is phosphoric acid here. For phosphoric acid, it's a triprotic acid. So in a triprotic acid, how many equivalence points should we observe? Well, a triprotic acid, we should observe 3. And so neutralize the first hydrogen, takes this much space. Neutralize the second hydrogen, takes twice as much. So it takes 10 milliliters to neutralize the first, another 10 milliliters to neutralize the second. And so when we hit to 30, we should be at the third equivalence point, right? But where is the third equivalence point here? The third equivalence point is not observed. What is the reason for that? Well, it's the same reason for this. The first equivalence point might not be observed either. Because this is fairly concentrated. This is a pH of 1.8, roughly. But let's say I just added more and more water to dilute it. Phosphoric acid, it was being stubborn, I couldn't get it to dissolve. So I just keep adding more and more water to my initial phosphoric acid, and let's say I started at pH 5 because I just dumped in 100 mils or 200 mils of water, ended up at pH 5. If I end up at pH 5, is there any way pH can go down with the addition of strong base? No, the only way it's going to go is up. So if the pH goes up from 5, am I even going to see the first equivalence point? No, I'm not. I'm going to miss the first equivalence point because the pH is too high to see it, right? And so this is why I recommend try to get it concentrated so that this becomes more pronounced, because usually this is not from experimental data. This is very clearly observed here, but in your actual experimental data, it might not be so clearly observed. Okay, and then in theory we should see the third one, but we don't. You know why we don't? Because pure 0.100 molar sodium hydroxide. You know what the pH of pure 0.100 molar sodium hydroxide is? Yeah, it's 13. It's pH 13. Well, the what's going to happen is you can take that pure and then react some of it with acid until all that acid's gone. Solution dilution. So are you ever going to hit pH 13? It's impossible to hit pH 13 because, well, I shouldn't say, at infinite milliliters, then we should approach pH 13. Right? It turns out that the third equivalence point is going to be about 12.8 pH. So we can't get high enough pH. It's not concentrated enough. We need highly concentrated sodium hydroxide to bring the pH up high enough to see. And so this is the difference in terms of like theoretically, yeah, but in practice, when you're doing it experimentally, you don't always observe it. And yeah, things come out different, between, let's say, what you calculate and what's observed. So for example, you guys calculated the pH of these solutions that you tested, yesterday, before. Were those pretty accurate, those calculations? Were your pHs spot on? No, what kind of percent errors did you have? Well, kind of big, right? Some of them, you probably had pretty big error, like boiling water. Boiling water should be pH 7. And so somebody's going to ask you, okay, must be a calculation error? Did you make a mistake in calculation? Or did you make a mistake in pH? What went wrong? Why don't your calculated pHs match the experimental pHs? And so what's going to happen as you continue in science is, before you just ignore that type of stuff, it's experimental error, calculation error, something like that. But eventually somebody's going to question you about this. Why is it different? Shouldn't it be the same? What's going on here?
And then you have to give an answer. You can't just sweep it under the rug and say that's experimental error. You have to come up with some kind of sound reason why. What would be my answer? Well, my answer, see, I'd have to think about it. I'd have to think about it because it depends. For example, if it's boiled water, it might be the, this is what some people said this morning, CO2 might recontaminate it. It could, but you know, you got to make sure you get rid of, but it shouldn't matter too much. You know, my answer is this is what causes, like in, I'll tell you, this is what causes a lot of problems. If there were simple answers to everything like this, then I would have been done with graduate school long ago. The problem is the data, you get questions like this, the data doesn't match what, you know, you're predicting at all. And so what's wrong? Is the calculation wrong? Is the theory wrong? Or is the data collection wrong? And so the answer is not easy for something like that. You know, and then you might compare your pH readings with your neighbor's pH readings and they might be different. And so why are they different and who's right? Both of you calibrated maybe with the same buffer. You know, is it the buffer that was bad? And so these are all things that have to be sorted out because you want to figure out what is right, where did it go wrong? Why didn't that calculation work out? And these are the toughest questions to answer in science. It's really easy to do the calculation, but you know, it's really hard if you don't know what the number means in terms of, you know, how it applies to and why we didn't observe it. You know, why didn't we observe that number? It should have worked. Calculation was right. The pH meter was calibrated. Why didn't it work? It could be because the stockroom's sloppy, right? You blame it on somebody else. It's always the best, right? We got to hire a new stock tech or something, some additional help back there. But those questions pose big headaches. I've had to deal with those big headaches a lot. So anyway, we'll stop here.